All right, well, hello everyone. I am going to be doing a talk on lightweight transactions here. So I am a developer advocate for DataStax. That basically means I get to travel around talking, doing cool things, and just generally goofing off for work, which is kind of awesome. They basically pay me to do what I would be doing anyway. So right now, well, here, I'll get into it. So we are working for the Empire today. We're the bad guys. We like being the bad guys. My Star Trek presentation is actually for the Borg, because there's a lot of good parallels between Cassandra distributed systems and Borg, but for the couple Trekkie nerds out there. So basically, as the Empire, we have some issues with data storage. You know, we have a big fleet, and this big fleet has a lot of different pieces of data coming from a lot of different places. They need it all to be consistent. You know, they're using it to actually make some pretty big strategic decisions. It all needs to be current, and we can't really have any errors. So kind of a big undertaking, a big task here, you know, much bigger than probably almost anything else we've done to date. So failure is not really an option. There's some pretty stiff penalties here, so we've really got to make sure we're choosing the right solutions to fit our problems. So some of the specific challenges. There's many updates from many sources. We can't have any downtime. You know, downtime equals really bad things, especially when there's lasers flying and that kind of thing. Data needs to be accurate. Obviously, like I said, it's being used for decision making, and some of it is pretty important stuff. And then fast SLAs. We can't be sitting there waiting for a year for a job to complete that we really need the info now from. So we did get some contractors in there, and it kind of resulted in some outages, downtime. Generally wasn't a good experience. So we're not really into this whole SQL world anymore. We're kind of thinking outside the box. So enter Cassandra. Cassandra, as we all know, is a distributed database, linearly scalable. We'll kind of get into it a little bit here. I'm going to cover some basic terminology. I assume most of the people in the room probably know how this all works, but just as a quick refresher, and then we'll kind of get into the crazy specifics that are pretty good. And if there are any questions at any point here, feel free to raise your hand and grill me. And if you know something I don't, you might get a T-shirt or something. So, all right. So terminology. We have nodes. Nodes are individual actors within a Cassandra cluster. It's a single instance or install of Cassandra. Each node is part of a data center. A data center is a logical grouping of nodes. It's not necessarily a physical data center somewhere. It could be AWS, could be anywhere in the cloud. Like, we really don't care. We're agnostic to that. It's just our logical grouping of nodes. Each cluster then can have multiple data centers in it. So each, this is a single cluster, this is a single database, but we're spread out over two separate locations. In this case, we're kind of looking for the fleet to each have their own data center on each of the ships, and have one cluster across the entire empire. So as you can see, we're fairly spread out. Basically, everything you see there that has names filled in is where we're working. So geolocation is very important. We have a lot of issues around, we don't need all of this minor system data from this planet to be on all of our planets. So things like key space replication factor actually become very key. And that's why Cassandra is really a good fit for what we're doing. Now, Cassandra being multi-data center means that we actually have the ability to be active-active. This is probably the biggest selling point in this situation. Mainly because, as I showed you, we're really spread out, and we actually need to do reads, writes from anywhere against our Cassandra cluster. So we're not, inputting and then only reading from one location, or we're very, it frees us up to consume this data that we're generating how we see fit. So very important. Linearly scalable is also a really big important thing. As we're building out the Empire, building out our fleet, obviously, the sensor data, the data from different worlds, as we take over more worlds, becomes much greater, and it grows. So we need this solution to scale with us. So again, Cassandra is perfect. And then fault tolerance. Things don't always go as planned, and as we saw from those previous SQL contractors who came in there, outages happen, and we want to be able to stay up even when they do. So we have an issue here, though. So for our decision-making processes, we need to be able to provide some guarantees. And these guarantees are the TIE fighters we think we're launching are being launched. They aren't actually blown up. We need to be able to figure out what stormtroopers are available, what ones are alive, what ones maybe ran into a group of Ewoks or something. Like, we need to know these things, and we need it to be fairly accurate. So we need to provide some guarantees. And Cassandra out of the box can't absolutely guarantee. It is good consistency. I mean, we're not sitting there going, oh no, like we're having to wait seconds for updates between data centers. We're not dealing with that problem, but we still need some guarantees against some of this stuff. And as we talked about before, bad decision making results in bad things for us. So what this means is Cassandra fits in the AP part of the CAP theorem, and CAP theorem is basically the concept that you can pick two of any of these for any database solution. So you're going to live with Cassandra, you're basically stuck in AP. Now you see up there we've got Bigtable, Mongo, HBase, Redis. Those are all CP, which is consistent and partition tolerant, which consistency is what we're obviously lacking, that we need more of. So enter the Cassandra lightweight transaction. That actually shifts us. We're giving up some availability for better consistency. So Cassandra lightweight transactions are actually ACID-like. Now they aren't ACID like if you're thinking, oh, this is a relational database ACID transaction. No, not exactly. It's actually more of a compare set sort of thing. And we don't actually offer like the rollback or any of those features that you'd get in the relational database world. But they do provide us with certain guarantees when we're writing, and we'll kind of get into some of the caveats there. So I have a terrible time actually pronouncing these whenever I'm up on stage, so I'm just going to let you guys read them. This is basically the acronym for ACID. This is what it means, and we'll jump into it a little bit. So lightweight transactions don't really change the atomicity, I think, is how it's pronounced, of the transaction. So this isn't really where the focus is of our efforts here, but it is part of ACID, so I did want to put it up there that we're not just skipping over parts. Let's see. We've got consistency. Now this is the one we're chasing after, right? We're trying to provide guarantees in consistency that what we wrote will be written, and in a distributed system, things won't be out of sync. And we'll get into a couple scenarios where things can be out of sync with normal read-writes. There is actually an interesting thing with this. You can provide pretty close to a lightweight transaction guarantee without a lightweight transaction by messing with your consistency level, but you're never quite going to get all the way there. You can do pretty close, though. Isolation. So basically, this is where that compare and set value comes in. We're actually able to test for existing values. It's kind of the if clause, and I'll cover that. But this is actually where lightweight transactions provide a unique capability that you don't have otherwise in Cassandra. And lastly, we have durability. Basically, this is one of the reasons you would use Cassandra. This is commit log, hints. These are all mechanisms to actually help with durability. So, all right. So, in a relational world where you have a single box, it's actually pretty easy to make some guarantees on things. You don't have to go out and get a whole bunch of different instances, pure instances, to agree on something to write something. You basically write and you say, yes, it wrote, no, it didn't, and you're kind of done. In a distributed world, though, it becomes way more complex because you're not just talking to a single object anymore. You're talking to potentially hundreds and hundreds of instances. And they all need to be able to provide the right information to each other so that you don't end up with overwrites if, say, something was trying to hit the same row. And so that's where Paxos comes in. Paxos is basically the kind of the easy way to make these guarantees. And it requires 4 different major steps. basically a preparation note, a promise, a read results, proposal accept, and commit acknowledge. And then once all of those steps pass, you actually end up with the yes, this wrote, no, this didn't, and life moves on. That slows you down, though. As you saw there are 4 steps, and there's actually a latency cost to that. So when you're actually using these transactions, your lightweight versus non-lightweight is going to have 3 to 4 times the latency because you got your network, you've got some decision making that's going on, you've got that whole compare operation we talked about earlier. That all has to happen that wouldn't under a normal Cassandra transaction. Normally, if you do an insert in a Cassandra world, it just does an upsert if there's something already there, or like we just don't care. We just throw things at it, and it goes super, super fast. Lightweight transactions actually takes a lot more into consideration before it finishes. So consistency levels. We're all familiar with quorum and local quorum, the 51% kind of rule within a data center or as a whole. Probably everyone here, or most everyone here, is using local quorum for what they're doing if they have a cluster. If not, I'd actually be very interested to hear why and what your use case is. Lightweight transactions, however, have 2 roughly equivalent consistency levels. That's serial and local serial. And those basically say this transaction will be handled under the construct of the lightweight transaction. So it's going to be handled slightly differently. But the 51% rule still applies. So you still need that number of nodes, the 51%. If you have like RF3, you still need 2 replies for a success and everything as you would expect. All right, so insert and update. They require use of the if clause. And that's, we'll actually show you a little more on that in a second. The if clause forces operational uniqueness. Basically, this is that compare and set. We're actually going to test for a value. If that value is there, we will succeed. If not, we'll fail. Operators, we have a lot of the operators you should be used to, the greater than, equal to, all that stuff is usable. The only one that always trips me up, and it's always the one that I go and look at the docs after I've been banging my head against my keyboard, is the in clause, because I'm always thinking equal, but it's always ends up being in. But essentially, it would function the same as what you'd think an equal would. All right, so here's where it gets kind of juicy. So what we're doing here, we've got an insert into our Death Star data systemetrics table. We've got our ID of the system. We've got it's our super laser, and it's operational. You also see the if not exists at the end there. That is your if statement. That's basically what says, hey, I'm a lightweight transaction. Process me like a lightweight transaction. And then the really cool one is update, where we're doing update Death Star data TIE fighter status. And we're setting a status to active on that particular TIE fighter if its status is fielded and active. Now, if that status was destroyed or maybe unfueled inactive or anything else, we don't want to set that to active because that's not going to be an operational TIE fighter. And if something were to happen, like some rebel scum were to creep in and blow that TIE fighter up at the exact time we were trying to set it to active, and so we have a conflicting piece of information hitting our database saying, oh, this is actually an inactive TIE fighter or a destroyed TIE fighter, we would want that to be taken into account. So whichever message gets there first will be the one that gets written. All right. Now this gets into the big caveat, the big gotcha in lightweight transactions. I've seen a lot of people misusing them in this way, and it results in some really bad stuff. Basically, if you use normal transactions and lightweight transactions on the same table, you are essentially sabotaging yourself because the normal transactions will not respect any of the blocking. They don't respect any of the process or procedure that the lightweight transactions have in place. What that means is if I do a normal transaction that's writing to a row, and I have a lightweight transaction that's in the process of writing to a row, it's just going to do its normal transaction, and we have to live with the consequences. So you can end up with some really bad anti-pattern stuff going on here if you end up writing them against the same tables. So kind of best rule of thumb, and a lot of docs, there's blog posts on this out there, there's white papers on this, and everyone's in agreement. Lightweight transaction tables are for lightweight transactions and make normal table for normal transactions and just keep them very, very separate. Okay, so in summary here, CAP theorem, we're basically moving from that AP to a CP, making it giving up our availability for a stronger consistency. We still get all the other benefits from having Cassandra. We get the data center, we get the tolerance, we get everything we would choose Cassandra for. We're just having to give up a slight bit of availability in those increased latencies, the slightly slower system, but we end up with a much more consistent result. The lightweight transactions are not ACID, but they offer ACID-like guarantees. They use the Paxos protocol to achieve that. They're 3 to 4 times slower than your normal non-lightweight operations. They have their own consistency levels, which are those serial levels I showed you. And just don't mix them with normal transactions. Just a good idea not to do it. That went way faster than it did last time I presented this. So there's more resources here. DataStax Academy, I've always got to plug it. That was my first exposure before I ever got hired at DataStax to Cassandra. It's a really good resource. I know a lot of people who use it who have no affiliation with DataStax at all. If you want to reach me or connect with me on LinkedIn, there's my info. We did start a DataStax Academy Twitch stream. If anyone's interested in live coding stuff, we have educational sessions where I get to go on and ask all my stupid questions to senior programmers who get to tell me why I'm wrong. So there's those resources, and join the empire today. We're hiring. So any questions?
Got a question?
Yeah.
So with traditional transactions and relational databases, I'm used to the ability of doing multiple things in a transaction. So update this row, update that row, so forth and so forth. Right. What limitations does lightweight transactions have in terms of updating multiple things within a...
Like a batch?
Yeah, something like that.
Yeah, so I believe, let me see if I get this straight. I believe you can do a batch statement with a lightweight transaction, but I think you're limited to a single lightweight transaction per batch statement, and it still will fail or succeed as a whole. So if your lightweight transaction were to fail, then all of your normal transactions against all your other tables would fail as well. That is a if memory serves answer, though.
Another question for you, sorry.
Yeah.
So if you start a query and it's got the if clause on it, so it's going to be a lightweight transaction, and there is another lightweight transaction in process,
yeah.
While it happens, does it just delay until the existing transaction completes? And is there any kind of timeout, or what happens in those scenarios?
Yeah, so there's a scoring system, and the scoring system is something I've read through many times and still can't tell you exactly how it works. But basically, there's a number that each of them gets that's their score, and one of them will win over the other. I believe the other one just gets an error back because it is essentially a block.
And then, what happens if? So you had an if clause. What happens if the if clause is not met? Say.
Oh yeah, failed if clause, like the TIE fighter was destroyed and I was trying to do that update. Yeah, I believe it, let's see. Actually, you probably know the answer to this one, don't you? You're trying to trip me.
Yeah, no, you're right. I guess the main thing is it doesn't actually fail, but there's something on the result of the query which tells you whether or not it succeeded. Yeah,
it was committed or it wasn't, basically, yeah.
I think a lot of what people will do is in order to know what to put in that if clause, they need to know what the data already is. And not in all cases, but in some cases. So they'll want to know okay, I made this change. Did it actually get applied? And then if it didn't, right, do something else kind of thing. So
yeah.
Just a quick correction, you can't have multiple lightweight transactions in the same batch statement. The restrictions, you have to be operating within the same partition.
Oh, yeah, that's fair.
And so
that is fair.
Hopefully, or relatively that least you always want to be operating within the same partition anytime you're doing a batch, because otherwise you have to deal with the coordination of spanning that out.
Right.
Especially so lightweight transactions don't want to.
Right.
In the case of multiples, if any of them fail,
yeah.
Another interesting thing is the isolation part, because I always get confused by, because like you can still see things happen that may potentially get rolled back or never applied if you're querying at the same time, which is really kind of interesting. Like I get to see like there's not the reason why they call it lightweight transactions, right? Because you don't get full power. But
Right. It's not the heavy transaction. I think is the relational world equivalent.
although it's called like normal transactions, but yeah,
Well,
I guess,
yeah.
yeah. Like, it's gonna be so expensive. I mean, the reason why we don't have full transactions, so expensive to do that in a distributed system, right?
Right.
Yeah.
Right. Yeah. Everything you do requires extra network hops, basically. Yeah.
So you may not know this question, but if I have multiple lightweight transactions happening on a same partition in a batch, and let's say I get through 3 of the 4, and the 4th one fails, and they all fail as a result of that, are any of the first 3 applied, or are they all, or do they roll back? That roll back. Yeah,
It's more of a
really good slide in Paxos phases. Okay. So they're not
Yeah, the
actually
Paxos.
applied during the read path until commit. And the commit doesn't happen until fail pass.
And they have that whole batch
Yeah.
log thing, right? So it doesn't actually get written until the.
Yeah. It basically respects your normal batch, like in Cassandra. Yeah. Yeah.
So we've got a space battle going on here, and I've got one Death Star over here, one Death Star over here. There is obviously latency across light years of space and so forth. They're both querying about the same object at the same time, and this one has done the lightweight transaction, whatever, and says if it's not dead yet. And this one commits one, or sends that query at the same time if it's not dead yet. This one makes this update. It's not dead. It happens. It starts getting fueled up. And this one doesn't know yet that this one got destroyed while it was being fueled up. My question is, as we start querying, okay, who's alive now? I'm in the middle of iterating over a cursor of TIE fighters or whatever that was that are currently alive, and this one dies in the middle of iterating over those cursors. How long does it take for this information to get from one and this node?
Like latency on the wire, sort of thing.
Yeah, this node knows that it exploded, and this node doesn't know that it exploded yet. I mean, tell me about that getting resolved.
Yeah, so that's actually kind of one of the, I guess, keys of why to use a lightweight transaction right there. So with the prepare promise right there, we initiate a file, or not a file lock, that's not right. We initiate a lock. And so when that second request that was like nearly concurrent, you know, it might have hit that node over there first, but then these two have not. Right, they're both asking at the same time. No one's written at that point. We have to get to the whole commit step right there at the end before anyone actually goes, okay, this is the data I'm writing, it's written. So at that point, with the prepare and promise, if there's a conflict where, you know, 2 different ones are in the works, that's where that scoring mechanism I was talking about will determine which one wins and which one fails. So you got one that fails, one that wins, and then the node that had the failing one will then receive the info for the winning one. So it'll bring that whole thing through, and then the rest of it just goes through normally. You know, the read results, pros accept, all that happens normally, and the actual commit happens at the end.
My row has been updated. My TIE fighter has been destroyed as I'm iterating over my things, giving orders out.
That's what you're saying. Basically, it's like
I'm just bitching.
like the
Okay,
state-
yeah,
the
I'm-
data changes before the transaction happens. And this is where like the consistency levels are really helpful too. Like if you want to do cross data center, you should use serial if you want to keep things
Right.
consistent state. But you're right. If the state had changed between when you start reading it, okay, I read everything, the state changed. I tried to do lightweight transaction. It should fail as long as everything's using the same consistency level because the state changed. Like even if you say, okay, if it was destroyed, if it was not destroyed, you say if not destroyed, and then it got destroyed between when you queried it and when you do the update, then it wouldn't apply.
Yeah, that wouldn't apply. But this is also kind of a key thing to note, that big warning slide I had. If you ran one of those as a lightweight and one of those as not, suddenly you'd be in big trouble, because like I said, the normal transaction wouldn't respect the lock, and it would just go, oh, okay, done. And who knows? Depending on where that was in the process, you could end up with all sorts of stuff. So
There's another very sharp edge there too, which is not very obvious, which is because Cassandra is all like timestamp driven in terms of like what's the latest data. Traditionally, when you do like an insert or update, the timestamp that is used is from the client that made the request. And when you use
Also problematic again with relativity.
yeah, that's why when you use like transactions, the timestamp is always from the server. Like even if you provide a client timestamp, it'll sort of away and say we need to use a timestamp from the server. It's basically an auto-incrementing timestamp. So like the next transaction will always be considered newer than the old transaction, where that doesn't exist with traditional non-LWTs. So like if you're mixing the both and your client's like way out of sync with your server, you can get in a weird state where like a client level request that you did like 5 minutes ago can take over the Paxos, or sorry, the LWT one. So you can get some really weird scenarios. That's why that warning slide you had like was very appropriate, because there are so many weird sharp edges that like
yeah, just don't mix them, basically.
Yeah, just don't do it.
You know, this actually does bring up an interesting thing I haven't thought of before, and you might know the answer, so this is me asking you a question. If you have two local serial against the same table, same row, different data centers, and different pieces of information, how does that actually justify? Because I can tell you in the just pure serial world, that's really easy, but in the local serial world, you'd end up with normal Cassandra replication happening, but then is it just timestamps then that would be respected, or how does that actually play out?
So basically, if you have client A, which is running that transaction against data center A, and client B against, you probably wouldn't want to use local serial in that case if you want to have cross data center.
Active.
You basically need to use serial, or else you're going to risk the case of, hey, everything's good in this data center, everything's good in this data center. Oh no, that or not.
Right.
But that might not be a problem for you, depending on your requirements.
Yeah.
It probably wouldn't be though. If you're using like a transaction, you probably have very strict requirements in the first place, right?
Right. Yeah, that's an interesting sharp edge that just like popped in my brain. But any other ones? Cool. Well, thank you.